an associate professor in the School of Cybersecurity and Privacy, and also in electrical and computer engineering. So his area of expertise is security and privacy of cyber-physical systems. He has led a very distinguished career, so received the Presidential Early Career Award for Scientists and Engineers from the White House, and the NSF Career Award and many others. So I would like to highlight the fact that he has a Google Hall of Fame award, and also an NSA Significant Research Award. So we don't see this too often, right? And then let's see. So today we're going to hear about his research, and we're really delighted to have you with us. So you have an eager audience.
Thank you so much, and thank you all for being here. Thanks for hosting me, Nico, and the great discussions we had before this talk earlier today. So I did my PhD at Illinois, but I was thinking the kind of connections I have at Michigan. I actually talked to a few of you. I thought I would put on a slide to just summarize. So John Mayer is my grand academic grandfather. He's a student, he was a UCS Michigan professor. And Bill Sanders, who is now president of RIT, before that, he was a professor at UIUC and department chair at ECE there. And then dean of engineering at CNU was his student, and I'm his student from Illinois. And then Farnam, who was also faculty at Michigan here for almost two decades now, president of CNU. His student, Michael Bailey, was our founding chair at the school with the department. I am a faculty, the School of Cybersecurity and Privacy. And now he just stepped down. He's a faculty now in our department. So I have essentially doubly linked, now triply linked. I also collaborate with Nico nowadays. So I think with that said, a lot of linkage to Michigan. So essentially at a very high level, what I thought I would talk about today is just sharing my vision about security of engineering system, and actually get feedback from you all during the talk. If you have any questions, let me know. If you have any comment, I would appreciate. And talking about what my lab does in research, kind of briefly through the challenges that we have had in the past, currently, and concerns of future. So essentially, as I said, sharing my vision on how to build a cyber-enabled, secure, safe society for good. And as I said, I'll look back at broken past and how we have taken initiatives to address some of those cybersecurity problems in engineering systems, and present challenges and future concerns that we should be planning for them today. And I was actually talking to Jeff earlier when we talk about critical infrastructures, and critical infrastructure actually being the focus to set the scope of my talk. That is my research focus, cybersecurity of critical infrastructures that by definition serve core societal functionalities like water, power, healthcare, manufacturing, and 16 sectors of critical infrastructures defined by Department of Homeland Security. So these critical infrastructures are, for example, the power grid, are so complex and huge and complicated, and attack vectors, when we think about cybersecurity, are so advanced nowadays that the traditional way of thinking about, I'm going to create the system to be absolutely secure to prevent attacks from happening and keeping all the attacks outside of my perimeter, is just practically infeasible. So attacks will happen, will succeed. Now, the question is how to deal with them. And that is essentially the definition of resilience that I will actually focus on. To identify the core functionalities of my system that must be maintained regardless of disruptions, either malicious or accidental. You may have extreme weathers in the power system, or you may have cyber attacks against the power system, or your controllers in the vehicle and other cyber physical platforms. So speaking of recently we haven't had enough of apparently incidents. We had supply chain issues because of pandemic. We had the CrowdStrike case in 2024 where a software bug caused airlines being impacted seriously. If you remember, the CrowdStrike case was a single security software update. The security software that was supposed to protect our security against threats, it was buggy, and it caused availability issues in airlines, and their core functionalities, flights were impacted without any threat. So even if we had not had it, we wouldn't have had that problem. So that is where like security and resilience, the system availability really sat across the table from each other, impacting daily lives of business and governments and $10 million. But also not only airlines got impacted, but multiple sectors because of interdependence across these sectors. I'll talk about that a bit more in detail, but I was also just talking with Jeff about how, for example, to run your water treatment plant, you need energy, and to run energy facilities and nuclear plants, you need water. And actually, along those lines, actually, more recent case of Iran war, to highlight how critical infrastructure that you guys all have been hearing about, like critical infrastructure being popular targets for different kinds of kinetic and cyber attacks. The start of the war started by U.S. Attacking Iranian telecom to blind their leadership to attack and kill their supreme leader. And then a month later, Iran retaliates. I'll talk about that. Cyber attacking against U.S. controllers, programmable logic controllers, PLC controllers in different critical infrastructure sectors in the U.S. And then earlier this month, now, if you just heard, I'm sure that the U.S. warns to hit several sectors of Iranian critical infrastructures. And then even currently what's going on in the blockade of Strait of Hormuz, where the maritime disruption paralyzed the energy sector. So the energy, essentially, that I just want to use that as an example of how different sectors depend on each other. The energy depends on transportation, in this case, maritime. And then in a lot of like Arab Gulf states, desalination plants, they are energy intensive, and Iran attacking different facilities there also affect the water indirectly. So the whole point of the two main points I want to talk about today particularly is the resilience, which is how to deal with attacks when they happen, as opposed to just trying to prevent them 100% out of perimeter, and the interdependence that is a challenge in addressing that resilience nowadays. So starting with past and challenges that in the past we took care of. The first one was the way we used to handle cybersecurity in platforms was by obscurity, essentially hiding cyber vulnerabilities as opposed to fixing them. We didn't have enough cybersecurity standards, and that resulted in inadequate and kind of inconsistent implementation of security, occasional protections here and there, a lot of holes left open. And then we didn't have enough redundancy. I'll talk about that. Like, in order to be able to cope with attacks, resilience definitions I just mentioned, you need to have redundancy. Either hardware, algorithmic. You cannot run your system at the capacity and then expect to have resilience. If something fails, you don't have any extra resources to bring it up and recover from that failure. And also a lot of vendors, particularly my focus is on cybersecurity of controllers in vehicles, in industrial control systems, PLCs, programmable logic controllers. I'll talk about them. They did not used to have security at all. And that has been actually addressed. I'll talk about that in a second. But in terms of initiatives that have been successful, I was talking to Vladimir earlier today. In power system, we have this what if scenarios and contingency analyses that is now mandatory by Department of Energy and NERC, particularly N-1 contingency analysis that says, if my system has N components, my power system has N generators, it has to be operational if I lose any one of them for any reason. So I need to have enough redundancy so that if one of the generators goes off, I can dispatch other generators to generate power to satisfy the consumption and the needs, power load, so-called. In terms of guidelines and the standards, now we have, this is old, but NIST, ICS, Industrial Control System Security guidelines are there. The Purdue model is there that for those of you, I guess most of you are familiar, the industrial control settings are kind of layered in terms of their functionalities. From the bottom layer, so-called kind of connected to OT, operational technology, sensing and actuation that is controlling and monitoring a physical plant like a power system, in drone case, the flight, or water treatment plant, connected to direct controller, PLC or programmable logic controller, and then all the way to kind of business functionalities and internet-facing network segments that the layered, segregated by firewall rules architecture, the Purdue model, so-called, is a famous traditional guideline for people to follow. And then MITRE ATT&CK framework, that's another one more recently by MITRE from DHS. And in terms of requirements, essentially, then the government has started from this best effort guidelines. They have moved towards mandatory cybersecurity requirements, CMMC, NERC-CIP, North Electric Reliability Corporation, critical infrastructure protection. Those are like hundreds of pages of mandatory cybersecurity requirements for the power grid. And I'll talk about that. That has been in like effective 2008, now almost 20 years. Power utilities that are all, they must comply with these, otherwise they get penalized heavily. Oil and gas follows TSA, and HIPAA for healthcare and CMC for manufacturing. So that's essentially from the technical perspective. I'll talk about NERC-CIP particularly. We have done studies on that. How effective are they? Regulations for cybersecurity critical infrastructures. And then from the policy side, also the government has, in addition to support and funding, has stepped up from policy side. So starting from 2022, the White House document, like very high level guidelines for cybersecurity, that was followed by a PCAS report during Biden, February 24, that essentially they had like several recommendations in that document. The main one being understand your system first. For resilience in cyber-physical system and critical infrastructures, understand your system first. What are the core functionalities that you must have? So if I'm like, for example, driving a vehicle, my infotainment is not as critical as my braking system. So kind of understanding different components and functionalities of your system well. And then they also like suggested to have observatory for threat intelligence in critical infrastructures in the country. And then the DOE cybersecurity strategy around the same time actually appeared, which was saying, when you think about cybersecurity, don't think about from IT traditional way of doing it, which is to consider all the vulnerabilities and weaknesses equally important, but look at risk and their potential impact on the physical process safety to prioritize which vulnerabilities are more important to address first. So for example, if I have a particular vulnerability in a vehicle controller that is doing some logging and that is or infotainment system, as I mentioned, it's probably that less important if I have vulnerability in my braking system or like a cruise control system. Following our discussion with, I believe it was James. Hold on a second. And then more recently, DOE CSER earlier this year, actually last month, or like 2 months ago, I came up with more policy. I talked about NERC-CIP, which is the mandatory cybersecurity requirements for the power grid in the US. And that has been in place. All the utilities, like hundreds of utilities in the US, they must comply. The standards are developed. You can download them. The power operators implement them. They spend a lot of time collecting evidence to later annually be audited and provide auditors with those to kind of pass through them. It's a stressful process. And then what we did recently was to interview 20-something subject matter experts from government and industry who are directly in charge of either standard development of NERCSIP or power operators, utility operators in implementing those regulations, or auditors. Directly interviewing them and seeing what are the challenges that they have faced over the last almost 20 years of implementing these requirements. So at the very high level, in terms of compliance, I said 3 topics: compliance, auditing, and implementation of or development of those standards. In terms of compliance, a lot of those operators complain about they are very prescriptive, as opposed to telling us an outcome. I want my, for example, your system to be secure in this matter, and then let us decide how to implement it. But instead, they are very prescriptive because of legal reasons, so that they can, for litigation later, to penalize, and that results in unnecessary kind of micromanagement and getting updated over time. Bigger utilities, for example, in Georgia, we have Georgia Power, which is huge. They said before these requirements, we already had our own cybersecurity team. We were taking care of those, versus some other utilities that we talked to. They said, these, just tell me what to do, and I do them and then get done with it, because I don't have resources, I don't have people to do those. And then in terms of zero tolerance, the requirements are audited in a zero tolerance fashion. So there's a lot of documentation has to happen, which doesn't directly impact and improve cybersecurity. It is just collecting evidence to later satisfy and convince auditors that we did it. And there's no automated tools to do this. So essentially that results in a lot of effort and energy wasted, not to improve security, but just making sure that they pass auditing. In terms of auditors, I mentioned about the effort, unnecessary wasted energy. I'll talk about this in a second, but auditors, cybersecurity auditors, for power system, they usually come from IT background. They don't understand control systems. They don't understand control. They don't understand power systems. And some of the comments they make don't make sense. They complained, as I said, for example, treating different vulnerabilities in different parts of the system the same way. Whereas, of course, if I have vulnerability in a PLC, that's way more critical than if I have in a historian, for example, which yes, it's an important vulnerability, but my PLC is directly controlling the plant. And then the atmosphere is kind of punitive, not really constructive. The auditors got you kind of, everybody's really scared in those meetings, everybody in auditing sessions and stuff. And from the standard development perspective, people complained about the whole process being very slow. So with AI now, for example, utilities don't know what they do. What is the requirements for implementing AI? Nobody knows, and nobody can implement AI for that reason. The same thing with the cloud computing. It's been taking for years. So by the time they're out, stuff are kind of already obsolete. And when they are out, for example, for supply chain security, it is super vague. I said NERCSIP is like SIP 1, 2, 3, all that. Actually, it starts with 2. SIP 13, CIP 13, that is supply chain security. And it's like you have to have a process in place to take care of your supply chain security. Super vague. So there are also some complaints there for the regulation perspective. We have similar studies for maritime and different sectors. By the way, this is citation for the papers that we have published that has all the details. But the bottom line is in different sectors, you see similar concerns in terms of cybersecurity, but there's a huge difference across sectors in terms of maturity of cybersecurity, how they have been handled. Power system finance are way ahead in terms of cybersecurity and regulation, whereas maritime or water is they don't have resources. There's no cybersecurity usually in water, which is why you see the water plants are the ones usually hit by Iranian hackers, to be honest, in the US. But there's a big gap between maturity level because of resources they have, because of course, energy sector, if it gets attacked, all the other sectors are also indirectly gone because everything depends on energy. So that's essentially the past challenges. Moving to present, let me see, how am I doing time-wise? Yeah, I'm good. So the current challenge is actually the first one, as I said, the linkage or disconnect between IT and OT. A typical disconnect that you all, from control perspective, feel when a computer science, cybersecurity, software person talks about cybersecurity. That is the disconnect I'm talking about. When you treat cybersecurity of an OT platform, operation technology platform, a physical operation, a power system, a vehicle, without understanding physical process, physical dynamics, physical safety concerns and specification, just talk about like software that runs on different pieces of the controller. That's what I'm talking about. And that disconnect has been a matter of like last decade or two. So lots of initiatives on that have happened, and that gap has been smaller. Still, as I said, auditors are being kind of discussed to be lacking enough OT knowledge. From the supply chain, the current concern, which is actually a very open attack surface in critical infrastructures, as I'll talk about, how can I protect something that I don't know I have? And this is real. Like Siemens, we talked to Siemens and Rockwell, they don't know what software libraries their controllers have, which is surprising, but I'll talk about that in a second. A lot of these controllers are getting more and more interconnected. I'll talk about how web technologies are being embedded in them for convenience, but also it provides attack vectors for malware propagation and potential cascading failures. The one possible consequence of disjoint IT/OT is that inheriting cybersecurity from computer science background and software fields, being reactive and real time in detecting attacks is a good thing. In OT platforms, real time is already too late. I'll talk about how in software, for example, chase.com, if you detect attack, then on the login page, exactly when it happens, that's perfect because you can pause the login until they call the customer service and it's taken care of. But you cannot pause a physical process, OT process, because of physical momentum, physical inertia. So you have to be proactive from that perspective. But this reactiveness and real-timeness comes from inheriting cybersecurity from IP in OT. And then, for example, a lot of malware samples that we analyzed in my critical infrastructure course, we actually analyzed malware from Stuxnet, like malware that you all probably know. Stuxnet malware was discovered in 2010, designed by NSA and Mossad against Iran nuclear enrichment plants, and that series, still episodes are going on even today for the Iran nuclear enrichment plants. But from Stuxnet, Havix, Industry, these are different malwares over years. A lot of them, a majority of them happens by entering the system towards a social engineering effort. For example, tricking a power utility operator in Ukraine to download a Microsoft Word document that happens to be Trojan, and that is the entry point. And once the malicious code is in the network, those networks are usually plain open. There's no kind of zero trust architecture in them. So you can do lateral movements and just reach PLCs to impact underlying physical plants. I've been talking about PLC all the time. I believe most of you know what they are, but in a short description, they're like professional Raspberry Pis. They're more expensive with a lot of real-time properties, and I'm simplifying actually. That they have inputs coming from sensors of the physical plant, whatever they are, whatever the physical plant is, power system, water plants, oil and gas, healthcare, like even on trains, you actually see them. So the sensors come in, and then the logic on the CPU executes the logic that you write, the operator writes, programmable logic controllers, and then it actuates the actuation. Super simple way of looking at it is like you can develop a PLC to be a thermostat. The temperature comes in, you say if it's more than 80, turn on the AC. If it's less than 60, turn off the AC kind of thing. But these are operated, programmed by operators. And then you have a screen engineering workstation to develop the logic. And also you have HMI, human machine interface, there while the system is operating, the sensor measurements come in and the actuation goes to the physical plant from the HMI, human machine interface screens and iPads. The operators look to see what's happening in the plant. Everything is normal, safe. And these plants are often miles away. So this is the only channel modality of observing how the system performs. So back to present perils. I'm actually going back to what I just talked about here, destroying IT and supply chain inactivity, topic by topic. I'm sorry. So in order to show how a malware can cross the boundary between IT and OT, in a paper at NDSS, which is a cybersecurity conference, we developed a physics-aware malware that started by compromising a vulnerability on the IT side of the network and doing random movements until it infected a programmable logic controller, a PLC controller, and sat in its firmware as a rootkit, kind of stealthy from detection perspective. But it was physics aware, meaning that the malware itself was included an emulation of underlying physical plant, very simplified emulation of underlying physical plant dynamics. In order to know what is a bad input actuation to the plant to cause unsafe situation there, at the same time, to fabricate good-looking sensor measurements back to which operators screen, HMI, human machine interface that I mentioned, so that from the operator's perspective, they can see everything is normal while the actual system is really in trouble. And that kind of calls for better hybrid cyber-physical system modeling. And there's a lot of effort on this as well happening. Andre Platze, previously at CMU, now in Karlsruhe, has its own logic, Daniel Liberson, switch control, and several others actually. A lot of work is happening. In Sanjit Sesha, of course, in Berkeley, and Inigo, there's a lot of effort there happening. Furthermore, actually, too, this is a kind of funny story, to show this IT, OT kind of linkage and how attack can go from IT to OT and cause unsafe situations. We created this maritime testbed in the lab that you see here. But the student, a PhD student that is there, Ryan Pikren, was also undergrad at Georgia Tech. And while he was at Georgia Tech, he was just a hacker. He didn't know what is ethical, what's not. And before a football match between Georgia Tech and University of Georgia, they're like a big rivalry going on between them. Actually, we always lose for some reason. But on University of Georgia's online calendar, he hacked and put that message right at the date of the match. And then both schools being public, he got indicted of a felony, but not convicted. Hence, actually, he joined our lab later for as a PhD. And actually, it is later for a QE project, we had to get background security clearance for students who were working on that project. And his case took a lot longer than other students actually to come back clear. And then on that maritime testbed, essentially, like I won't actually spend more time on this, but we essentially showed how an IT through these CVEs for control people in the room. These are like software cybersecurity vulnerabilities that are timed and numbered by you kind of timestamp them, kind of thing. So every CB represents a vulnerability. Through IT vectors, we're able to get into the network of the ship. These are all in commercial products like Garmin, VHF radios, and MFDs, multi-function display, until it kind of got into OT operations of the ship in order to steer the ship as a malware remotely. This is actually later be used. This is very high level. Here we show how you use AIS protocol that is used in ships, in airplanes. You have ADSB that through AIS messages, ships say you're essentially broadcasting to ships around them about their location, but unencrypted. So this malware used AIS channel to propagate through ship by ship, and then using lower orbit satellite collected data for AIS from company Spire, the simulated if you have a ship infected, how many days does it take to have infected ships going through the choke points like Strait of Hormuz, for example. There are 8 of them in the world, and it takes like less than a month to get to. And you remember during, for example, pandemic in Suez Canal, huge ship really blocked the whole thing and causing supply chain issues, and how feasible such attacks can be based on real collected data. So the second point on present challenges, supply chain, I said, how can you protect something you don't know you have? And for that, we started by dissecting firmware images from PLCs from 6 commercial widely used vendors: Siemens, Rockwell, Allen Bradley, ABB, Schneider Electric, Micron, and one more I forget. But like more than 200 firmware samples, we analyze them to see what is in there. And then findings very interesting, kind of summarized here, that different PLC models from the same vendor, for example, Siemens has 2 PLCs, very famous 1200, 1500 series. They share a lot of code. In that case, almost 90% of the code is shared. What that says is if I have any security vulnerability in that shared code with the same exploit and attack vector, you can compromise both models. You don't need to redo your work. In Siemens PLCs, we had software libraries 14 years old. 6 years past that library's end of life, determined by the library developers. If you go across vendors, 13% of third-party software libraries are shared. Again, if you have a vulnerability in any of those shared libraries, you can exploit them with the same exploit. Even beyond that, as we have seen, actually, this is not hypothetical, last year it was discovered that the library called libxz or xzutils is a commonly used library in SSH authentication in Linux systems, had malicious code running in it as a backdoor by Chinese usernames. And what that means is like you have malicious code running in these potentially third-party libraries, and that infects controllers from different vendors. So there's a distinction between having a benign vulnerability that can be exploited by a remote adversarial attacker, and malicious code that is injected there already as a logic bomb can trigger whenever that wants. And then some controllers, a lot of libraries are working together, different versions. In software, if you update a library because it is buggy, you have to update many other libraries as well to take care of interdependencies. But they, for example, Schneider Electric in this case, decide to bundle and maintain several outdated versions together. And then a lot of vendors, they do in-house surgical fixing of libraries, as opposed to updating an old library to a new one, because it would require updating multiple other libraries and then costly unit testing. And that causes a lot of chaos, because a lot of those in-house fixing causes new vulnerabilities that we have actually identified. Any questions so far? Yes, please.
I thought private libraries really that much of a concern because, I mean, yeah, you can share them, but I guess they are a lot less likely to have vulnerabilities, right? Because like everyone uses them, right? So that's like a lot more, it's code that has a lot more eyes on it.
That is true. You can, like, for example, an example I can say, OpenSSL Heartbleed. OpenSSL is very widely used library. And the vulnerability card called Heartbleed is in OpenSSL. And once it was discovered, before it was actually announced, the dark web would know about it. And that vulnerability can be used to disclose the encryption keys. So back to your point, what I'm saying is like, there are actual cases of this. libxc was malicious backdoor, Heartbleed, but that is a kind of discussion of open software and
but it was also discovered because there were more eyes on it, right? That's how people actually found it, because someone like in Microsoft started using it, said like, oh, the performance doesn't match, right? So that is, I guess that they can have, I'm not saying they cannot, right?
Yes.
It also seems less likely, coming back to the your previous statement, like there will be attacks, but so they have
that's
assess the risk as well.
Absolutely. That I completely agree. Depending on if you find, for example, once you find a vulnerability, you have two options: one, to report it to CISA DHS and get a CD on it, or you sell in dark web, and they pay a lot.
Right.
So it depends on the person who discovers it. Is a good person or a bad person. But yeah, I totally agree. Like having open source, of course, everybody has an eye, including bad people too. So this essentially like third-party following guards models is yet another vector of interdependence across these PLCs, controllers in this case, and PLCs, as I mentioned, are used. The same PLC that you buy from Siemens is using water treatment plants, train the same device. So essentially across sectors also this shared vulnerable and malicious code, potentially supply chain backdoor code, can cause kind of aggregate exposure for attacks. I mentioned PLCs, and the third point on present challenges was interconnectivity. They're getting, it's not just about PLCs, it's all IoT devices. Buy any device to water your plant, there's a web app with it. And it is because there's a web server included in it. PLC is the same thing. These devices, IoT devices, industrial IoT devices, so-called, they have become powerhouses of functionalities, including web servers. That is there, as I mentioned, for convenience, but also provides attack malware propagation channels. We actually did study this in PLCs, actually, because of time, I'll probably skip about the details here. But the bottom line is, we leverage the fact that almost all PLCs in the market now have web servers in them. So as opposed to really reverse engineering the firmware executable binary to inject the malicious code in it, which will make it very specific to that PLC model and architecture, the hardware architecture, because there's a web server running on it, I can just have my malware as a JavaScript code. And we actually discovered some zero-day vulnerabilities and all that stuff. To be honest, which is not hard when you have a web server. Web is intrinsically very insecure. So this is the same Purdue model that I was talking about. And having this web-enabled PLCs, you're essentially replacing old-fashioned firewall-based segregation of Purdue model with whatever you can assume from web in terms of cybersecurity, which is, to be honest, not much. And then after we developed this Let me see if I can. I think it's coming back up. Okay. So after we developed this web-based malware, which is again agnostic to universally usable, because it doesn't depend on PLC model and firmware, image version, and all that. So then we wanted to see how exposed, how universal this problem is. Can we find exposed PLCs in internet worldwide? And that is the hypothesis we kind of tested. So we essentially did scan the whole internet. Like essentially the tools that you would use to do this, Shodan is a website for it, Census is another website for it, that gives you all the IP addresses, but what actually matters is the query that you put in there. So if you just put simple query Siemens PLC, that you may get like 100 results back. But then in this project, using like a lot of manual involvement to design queries and a bit of clustering and ML, and again, details are in the paper, but the bottom line is we found PLCs 37 times more compared to past 4 worldwide in governments, factories, airports, military hospitals, and power grids. And then we did like outreach back to them, asking them to take some of them off the internet. Very small percentage, less than 3% for honeypots. But then, 30% actually took that off the internet, which is great. A bit more specifically on the technical side, how that solution works is it's kind of iterative solution that optimizes the query and goes back and finds more devices. So it essentially starts with, if I actually bring them all here, actually. So it starts with a seed query that gets you 8 devices. And then based on those 8 devices, the system, the algorithm analyzes those returned device reports and then optimizes the query for the second iteration. So the first one returns back 1 PLC, and then gradually the second and third and fourth query increases the number of returned PLCs until kind of it plateaus. And it was around like 7,000 PLCs worldwide that we were able to find on, I think this was the brand Vago we can do for Siemens and Rockwell and others. And in a manual verification of those, not all of them, 100 of them, not actually several 100 that we had to manually analyze, it does well in terms of true positives in what returns. This was essentially PLC discovery. So essentially this kind of confirmed these web-enabled PLCs are all exposed, not all, but they are exposed in internet. I was talking earlier with, I think, Emily and Inigo, that we did outreach and to take hopefully them off the internet. I was also presenting this to defense contractors at Georgia Tech, and they said, this is great, we will fund them, but we just asked them not to report them back to the operators. We just give them a range of geographical regions to do this search and just give that list to us. And then earlier, actually this is April, earlier this month, we see this. No wonder all these PLCs are, there's no authentication. To be honest, in a lot of these PLC devices, you can run your malware in these PLCs and do whatever a legit operator can do, because security is non-existent in a lot of these platforms. Or if it does exist, it's not configured correctly. In a follow-up work, a second measurement we did, this is actually also, I was talking to Vladimir, this is with Dan Molzon, an optimization person at Georgia Tech, a power system person. So we did search for solar inverters and DRs, distributed energy resources, particularly solar inverters. So we found them all in internet, almost 90-something thousand of them. And then we used the power system model of Hawaii Oahu Island to analyze what can you do as an attacker only using our discovered solar inverters in this island. And the ones actually, it is surprising if I have the video, actually I can play if you want. What you can see, not only like hourly power consumption of like essentially what an admin can see, but also it's an admin website of the solar inverter. You can go and there's a button, would you like an update the firmware, or and you can actually upload your executable, and essentially you have your code running on that solar inverter, which allows you to change the power factor, whatever you want. But if you have a lot of them in control, you can do coordinated attack. And again, Dan Molzon's group doing optimization, we were able to cause undervoltage, overvoltage on any bus in Oahu Island independently, not simultaneously, using only the DRs and solar inverters that we were able to find and discover in Oahu, exposed in the internet. Again, left without authentication. I actually can provide more details if needed, but because of time, I'll actually skip. Probably I'll skip the future part and finish the present. I'll keep it, as I said, like a very summarize. The whole point of this slide is, as I mentioned, inheriting cybersecurity from IT. The solutions are reactive. Real-time detection is considered good. Where in OT, it's too late. You need to be proactive. And the way we at least try to handle it is by similar to like MPC, model predictive control, along those lines of, intuitively speaking, based on the current system state, the controller execution state, and the physical plant state, we perform reachability analysis on the system model, searching for potentially bad states coming up. And then if we see something coming up, then that time gap allows us to do something to hopefully proactively prevent it from happening. So that's the bottom line of what is happening here. That actually I can skip forward on that end. And then finally, the future concerns, think of cybersecurity, almost 500,000 open positions cybersecurity in the US, still not 25,000 graduates of cybersecurity are able to get jobs because of the gap between what we teach them and what the industry needs. This is actually, we had earlier discussions about it. Speaking of future, AI, hard to not talk about it. So it's about, like, you probably have heard about like Anthropic's Mythos AI and AI X competition DARPA challenge, where AI is used to discover vulnerabilities. If it's used by adversaries, you have 0 days in like attackers' hand against your system. But also it's about like when you have AI as as controller or as perception, that AI is full of unknown holes. Kind of asymmetric fashion for attack and defense. In order to defend something, you have to cover all the holes. In order to attack, you need just one hole. And AI, if you're using it in your system for control, perception, whatever, it's just full of unknown holes. That is kind of asymmetric there. Cross-sector resilience, I already talked about it. Nothing really to add there. And then over complex systems is, I talked about the cross-sector dependence causing complexity. I talked about PLCs are becoming powerhouses of functionalities. The same thing, to be honest, with all the industrial IoT platforms. And along those lines, like for example, if you have a collaboration with Inigo on using contracts that he's an expert on to compositionally verify all the ECUs operating with each other, interacting with each other in a given vehicle. If one of the ECUs gets compromised, what's the impact on the overall vehicle operation in terms of safety, and so on and so forth. So some of the initiatives that we have done in Georgia Tech, security of engineer systems, with course development, and we have faculty, for example, joint with aerospace, and we have online. I'm actually directing online cyber physical masters program. There, a lot of courses are there, including 3 courses like critical infrastructure that I teach, just like a bit high level, like talking about 9/11 and 2003 blackout and colonial pipeline kind of situation. Their intro to CPS is very hands-on with PLCs they program, and we analyze different malware, PLC malware, and like startup malware, and so on and so forth. And then finally, cybersecurity drones, where in a single syllabus, I teach half of the syllabus about like firmware security and software security and reverse engineering and supply chain attacks that they do hands-on, but also half of it is like control topics, system identification and common filtering and H-infinity controllers in case your sensors are problematic. And so kind of trying to bring all the components together. Also, this lab was impressive in terms of what they have done, but we actually use the same kind of drones, students hands-on in our outdoor flights. They actually use different, they get different pieces of the drone physically and open source firmware, holding actually similar to what Monas was talking, to compile it and calibrate the drones. And then two teams of students, one team is attacking while the other team during the drone's flight, trying to defend that attack. So it's kind of a fun topic. And they have fun while they learn these topics. One thing I was mentioning earlier is that based on my experience, half of the class who are in CS, half of the class engineering. Computer science students have more difficulty understanding control concepts and math dynamics compared to engineering students understanding firmware security and reversing concepts. That's at least my observation in the last 4 years of teaching this class. Essentially, bottom line, this is all our group. Obviously, big acknowledgement, thanks to them. This is Ryan, indicted of felony. We shared the lab with Rahim. He's now the provost in Georgia Tech. Animesh, our research scientist, and the rest PhD students. Big thanks to sponsors, and finally, I'll just conclude and stop here. So the whole point about resilience and topic is, the first thing is you have to understand, first off, absolute security is impossible. Attacks will happen. How we can recover from it requires design time, redundancy built in the system, and understanding what are the functionalities that I must maintain, regardless of disruptions that will happen, I know, and then doing it in a risk-informed fashion by prioritizing what matters, what doesn't matter, by bringing physical dynamics into the picture when I'm thinking about security of software in the controllers. I think with that, I'll stop. Thanks for your attention. Any questions, I'd be happy to.
But like with all this agentic AI stuff, how much they are increasing vulnerabilities and discovery of vulnerabilities? Is the time for discovery of vulnerabilities shrinking because of these agents out there?
That's an excellent question. So essentially, like my experience, and we have a lot of discussions in this about this in our faculty meeting. Like the two biggest or initiatives, one is DARPA challenge on AI, using agentic AI to discover vulnerabilities. And Kei-Soo Kim from our school won that competition. Now he's, for example, in Microsoft, that they're trying to put that in their model. And then the most recent one is from Anthropic Mythos, AI model that discovers vulnerability. Again, following what Monas just mentioned, depends on who uses it and who gets the most advanced AI model. If I have my software open and they use that AI model to find vulnerability in it, if those people are malicious, they won't announce it widely. They will use it to attack the systems. If it has good people, they will announce it to get them patched. Yes?
Maybe a follow-up, is CPS in a better place compared to like pure software in in terms of like being less vulnerable to these agents because like there's probably less data about CPS out there.
I see what you're saying. Based on our measurement studies, there's a much bigger problem. A lot of vulnerabilities and weaknesses and misconfigurations that do exist in critical infrastructure are very primitive. They can be fixed. Having PLCs exposed to internet, solar inverter exposed to internet is something that it's very easy to fix. You don't need Mythos. You don't need any agentic AI. So if I'm the adversary, supply chain attacks and those exposed controllers is the vector I will use to attack the systems. I don't need to use any of that, any of those agentic AIs. But what agentic AI have been able to do so far, for example, Mythos's Anthropic models kind of breakthrough is that it has been able to find vulnerabilities that are exploitable, because vulnerabilities have been found by past agentic models that are, yes, deep in my code of my controller, in my web server, I have a vulnerability, but in order from the input attacker-fed input to get to that vulnerability and exploit it, if it's not exploitable, that vulnerability is useless. But Mythos was the model for the first time that found a vulnerability that's exploitable. Whether that vulnerability was already discovered by humans previously, yes. But this was the first AI agentic model that was able to do it. So it is in the right path. But back to your question for cyber-physical systems, OT platforms, security is so lagging that you don't need any of agentic AI, to be honest, yet, I think. Good. Great, so that's clear.
Yeah, I have a question, if that's okay. We'll go back to the drones, right? And I see currently, DARPA and others, they start like to ask for mesh network autonomy, right? You have like 5, 10, 20 robots that they are, let's say, aerial drones, right? That they need to collaborate. We talk about coordination. It's just not just formation, not just about, random walks and blah, 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 but there is exchange of information. So communication will be present there. What do you see as the major vulnerabilities, and what are also the best defenses to that? Is it different communication modes, optical communication? Do you have any thoughts or insights to say?
I think that's an excellent question. Let me start with, okay, so that's not what I have worked on, but in the community, in the cybersecurity community, there are very preliminary efforts on, there's a paper called Swarm Flaw Finder from, I think, Maryland, UMD. There are a few papers on that, but it's not a well-explored topic. But the way I look at it is from the communication security perspective, they're like, depending on your threat model, what are you assuming the threat is capable of doing? If it is jamming, encryption, optical, you have no chance. In other words, you have to have a multi-agent platform that can operate completely distributed, if it's need to be the case. But if it is, again, 2004 in Iraq War, Iraqi insurgents were able to capture unencrypted video stream back to ground control station from US drones and just see what the intelligence they're gathering. So that can be, that kind of attack can be protected by end-to-end encryption. And key exchange, those protocols are all in place from cybersecurity perspective. So first off, I should be able to operate my drone without any communication. The algorithm should not require, for sure, communication between them. The second thing is, for example, the potential attack model that also has been explored in cybersecurity papers is if I have a malicious drone, if I have one of your drones compromised, from the algorithmic perspective, I'm not talking about software, from algorithmic perspective, is your swarm control algorithm resilient to that? Can I persuade other drones with a malicious drone to do something against the plan? And so everything depends on requires having a so-called threat model in terms of what I'm assuming the attacker can do. Can it compromise one of my drones? Is my algorithm robust? Okay, can it compromise two of the drones? Is the algorithm, can the attacker jam the communication channel? Can the attacker cause GPS spoofing, like sensor spoofing attacks and these kind of things? But I think the more challenging aspect of when you talk about SORM is from the semantic algorithmic security perspective.
Yeah.
Is it secure if I have some of the nodes compromised and do something against my algorithm?
Yeah. And just a quick follow, or I can follow up after. So thank you so much. Yeah, I appreciate that. Yeah.
Thanks. Thank you so much for listening.
For 30, so let us thank
I watched
I would like to.
but